Hello everyone, I am Zhichen and I will present our work Efficient 3D Gaussian Splatting with Axis-SharedRasterization and Order-Independent Transmittance. This work is a collaboration between Shanghai Jiao Tong University, the University of Cambridge, Imperial College London, and Samsung AUI. The goal is to make high-quality 3D Gaussian splatting practical on edge devices. We focus on inference acceleration. Once a 3DGS scene has been trained, the same scene is rendered many times from different viewpoints, so rendering efficiency directly determines interactive performance. 3D Gaussian splatting, or 3D DGS, represents a scene as a set of anisotropic Gaussian primitives. Each Gaussian stores learnable attributes, including position, shape, opacity, and view-dependent color. Training optimizes these primitives from multi-view images. After training, inference repeatedly renders novel views from new camera poses, and this is the critical path for interactive applications. For AR and VR headsets, robotics, and autonomous driving, local rendering is valuable because it reduces latency, avoids continuous cloud bandwidth, improves reliability, and keeps scene data private. The difficulty is that edge platforms operate under tight power and area budgets. For example, on an NVIDIA 8 Jetson or a Nano Edge GPU, 3DGS rendering reaches only about 20 frames per second on the MIPNERV 360 dataset. This motivates an accelerator design for 3DGS inference under resource-constrained edge settings. The 3DGS rendering pipeline contains three main stages. Projection maps each 3D Gaussian into screen space and computes its depth. In our profiling, it accounts for 14.2% of GPU latency. Sorting orders the Gaussians inside each tile by depth. It is required by front-to-back alpha blending and accounts for 25.3% of latency. Rasterization computes each Gaussian's opacity contribution to each pixel and accumulates the final color. It dominates the pipeline, taking 60.5% of latency. The equation on the right explains the dependence on sorting. Each color contribution is weighted by alpha and by transmittance, Ti. Since Ti is the product of all previously blended front Gaussians, the original pipeline must know the depth order. Sorting and rasterization together contribute almost 90% of the rendering latency, so they are the main optimization targets. The first challenge is redundant computation inside rasterization. A conventional accelerator maps one pixel to one PE. This mapping is highly parallel because all pixels in a tile can be processed at the same time. However, the mapping is not compute efficient. Each PE independently evaluates the full alpha expression for its own pixel, even though neighboring pixels share many intermediate terms. By expanding the alpha exponent, the computation can be separated into three parts: an x-axis quadratic term, a y-axis quadratic term, and a cross term. The x-axis term depends on the x-coordinate and the Gaussian center. The y-axis term depends on the y-coordinate and the Gaussian center. The cross term couples the two axes. Within a tile, pixels in the same row share the same y-coordinate, so the y-axis term is shared. Pixels in the same column share the same x-coordinate, so the x-axis term is shared. Conventional pixel-wise PE designs ignore this structure and recompute both axis-dependent terms in every PE. As a result, each alpha computation still requires 8 multiplications, 4 additions, and 1 exponential operation. The key problem is therefore not a lack of parallelism. Rasterization already has abundant pixel-level parallelism. The missing opportunity is axis-level reuse within each tile. The second challenge comes from sorting scalability and pipeline imbalance. After projection, different tiles contain very different numbers of Gaussians. Some tiles are sparse, while dense tiles can contain orders of magnitude more Gaussians. This variation makes fixed sorting hardware hard to size. Let n be the number of Gaussians in a tile. Rasterization is mainly NMAC dominated and scales approximately linearly, with n. Bitonic style sorting, by contrast, has superlinear complexity, roughly O of n log squared n. Because the two stages scale differently, a fixed hardware split cannot remain balanced across all tiles. A small sorter is efficient for sparse tiles, but becomes the bottleneck for dense tiles and forces rasterization to wait. A large sorter helps dense tiles, but wastes area and energy when the tile has few Gaussians. For an edge accelerator, simply scaling up the sorter is unattractive. A better direction is to replace sorting by directly computing the quantity It is used to obtain transmittance. We first address rasterization. The objective is to eliminate redundant computation inside a tile while preserving full pixel-level parallelism. Axis-SharedRasterization exploits the row-wise and column-wise reuse discussed earlier. The design keeps a 16 by 16 rasterization PE array, so each pixel in a 16 by 16 tile still has a dedicated PE and pixel-level parallelism is preserved. Two lightweight preprocessing lines are added around the array. The XPE line computes the x-axis shared terms for the 16 columns. The YPE line computes the y-axis shared terms for the 16 rows. The data flow has 3 steps. First, the XPE and YPE lines compute the axis-dependent terms once per Gaussian. Second, these terms are broadcast to the corresponding columns and rows. Third, each rasterization PE combines the received terms with the remaining cross term and completes alpha computation and blending. In this way, each PE no longer evaluates the entire alpha expression from scratch. It only computes the part unique to its pixel after the shared axis terms have been pre-computed. After amortizing the XPE and YPE overhead over the 16 by 16 array, the alpha computation cost drops from 8 multiplications and 4 additions to 2.31 multiplications, 2.33 additions per PE. This gives a 63% reduction for alpha computation and a 38% MAC reduction for full rasterization, while preserving tile-level parallelism. The next bottleneck is sorting. Rather than building a larger sorting engine, we revisit why sorting is needed in the first place. In the original 3DGS pipeline, depth sorting is required because alpha blending depends on front-to-back transmittance. For a Gaussian eye, the transmittance Ti represents how much contribution remains after all Gaussians in front of it have already been blended. Sorting is used to identify those front Gaussians and compute the cumulative product. The key observation is that sorting is only the mechanism. The actual quantity needed by blending is the decay factor, or transmittance, assigned to each Gaussian. This connects 3DGS to classical image composition. Although image composition is usually described back to front, and 3DGS uses a front-to-back formulation, expanding the equations yields the same final color. Traditional order-independent transparency avoids explicit depth ordering by estimating blending weights directly. We adapt this idea to 3DGS and estimate transmittance directly. However, plane depth-based weighting is insufficient for 3DGS. The representation is view-dependent, and occlusion behavior changes with camera direction. Therefore, the transmittance model should be view-aware while remaining hardware lightweight. Our OIT method predicts the decay factor directly, instead of computing it through an explicitly sorted sequence. During training, the MLP takes Gaussian depth di and view direction as input. The view direction helps capture view-dependent visibility and blending behavior. Training starts from a pre-trained 3DGS checkpoint. For each camera pose, Gaussians are projected, depths are extracted, and the MLP predicts transmittance factors. The renderer then produces an image using the OIT formulation, and the rendering loss updates the MLP together with a lightly fine-tuned Gaussian representation. The learning rates are intentionally different. The MLP uses a higher learning rate to learn the decay function quickly, while the Gaussians use a lower learning rate to preserve the original scene representation. At inference time, the runtime model becomes much simpler. For a fixed camera pose, the view contribution can be pre-computed and folded into the MLP biases. Therefore, the online MLP only takes depth as input. The final inference model has 2 layers, 10 parameters, and only 6 MACs per Gaussian. It reuses the arithmetic units already required for rasterization. Training is view-aware for quality, while inference is depth-only and hardware-friendly for efficiency. After optimizing rasterization and replacing sorting, the accelerator must support both rasterization and MLP-based transmittance prediction. The goal is to do this without a separate neural accelerator or a new pipeline bottleneck. The core of the architecture is a 16 by 16 reconfigurable PE array that supports 2 modes of rasterization and MLP inference. The XPE and YPE lines provide axis shared terms during rasterization. Broadcast registers distribute mode-dependent operands, such as opacity, color, predicted f of d, and MLP weights and biases. For storage, the GS feature cache stores projected Gaussian attributes. The depth buffer stores DI, and the predicted transmittance factor f of DI. The pixel output buffer accumulates intermediate results, and the division array produces final RGB colors. Reconfiguration is implemented with multiplexers on the PE data path. Each RPE contains 6 multipliers, 6 adders, and 1 exponential unit. The main point is that the OIT MLOP is not a standalone neural engine. It is mapped onto the same arithmetic fabric used for rasterization, which avoids extra hardware and maintains high utilization. At the PE level, the two modes share the same arithmetic resources. In rasterization mode, the PE receives precomputed x-axis and y-axis terms, computes alpha for its pixel, and accumulates the weighted RGB numerator and denominator for OIT blending. In MLP inference mode, the PE takes depth DI as input and evaluates the small transmittance prediction MLP. The predicted f of DI is written back to the depth buffer and reused during rasterization. Only the operand routing changes through multiplexers and broadcast registers. This unified design lets rasterization and transmittance prediction use the same PE array rather than competing for separate hardware resources. Although the inference MLP is tiny, executing all NLP operations as a separate bulk phase would be inefficient. The reason is operational intensity. Rasterization reuses each Gaussian across many pixels, so it performs substantial computation per byte loaded. NLP inference reads depth values and performs only a few AMACs, making it memory bound. We address this with a fine-grained interleaved pipeline. Each tile is divided into subtiles. While the current subtile is rasterized, the accelerator prefetches depths for the next subtile and writes back the corresponding f of d. After the first subtile, most depth access latency is hidden behind rasterization, keeping the reconfigurable PE array busy. Off-chip traffic is further reduced with a pi-trajectory tile schedule. Neighboring tiles often share many Gaussians, so tile traversal order strongly affects GS feature cache locality. The pi trajectory preserves horizontal, vertical, and hierarchical locality while avoiding long diagonal jumps. This improves the cache hit rate from 43% to 62% and reduces off-chip energy by 1.51 times over the baseline traversal and 1.3 times over Z traversal. This scheduling-only optimization improves locality without changing rendering quality. I will now summarize the evaluation. The key questions are rendering quality, the contribution of each optimization, and overall speed-up and energy efficiency. For algorithmic evaluation, we use MIPNERF 360 scenes and report PSNR at SSIM and LPIPS. The quality baselines include sorted 3DGS, weight sum blending, depth-only OIT, and our depth plus view OIT. For hardware evaluation, the accelerator is implemented in system Verilog using TSMC28 nanometer technology, FP16 data paths, and a 1 GHz clock. The design occupies 3.85 square millimeters, consumes 1.64 watts, includes 96 kilobytes of on-chips RAM, and contains 256 PEs. We compare against Jetson Orin 90 as an edge-class GPU and RTX 3090 as a desktop-class GPU. The quality results show that sorting can be removed with only a small impact on rendering fidelity. Axis-SharedRasterization is numerically identical to original rasterization, so any quality difference comes only from OIT. Our depth plus view OIT reaches 26.90 PSNR, only 0.31 below sorted 3D GS. SIM remains close, and LPIPS is better on average. It also outperforms depth-only OIT and weight sum blending, confirming that transmittance in 3D GS should not be modeled by depth alone. The visual comparison supports the metric results. In the highlighted regions, weight sum blending introduces visible artifacts, because its simple weighting does not capture local occlusion well. The MLP-based OIT result better preserves depth layering and appears closer to original sorted 3D GS. The same trend appears in the second group of examples. Weight sum still shows local blending artifacts, while MLP-based OIT more closely matches the sorted 3D GS reference. These two visual examples reinforce the main algorithmic message. Sorting-free rendering can preserve visual quality when the transmittance model is learned rather than manually fixed. The ablation study separates the contribution of each optimization. Axis-shared rasterization alone provides a 137 times GMEN throughput improvement by reducing redundant rasterization MACs. Adding OIT increases the gain to 2.16 times because explicit sorting is replaced by lightweight transmittance prediction. With the interleaved pipeline, the full design reaches 2.27 times by hiding the memory latency introduced by MLOP-based OIT. Together, AR, OIT, and IP target different bottlenecks and are complementary. The stage-level results explain where the speedup comes from. For rasterization, the Axis-shared PE design converts MAC reduction into real latency reduction, achieving 4.6 to 7.9 times speedup over the edge GPU. For sorting and OIT, interleaving is essential. A naive OIT implementation is still memory-bound. With fine-grained interleaving, the speedup increases from 21 to 119 times to 357 to 634 times. This confirms that replacing sorting must be paired with a pipeline design that hides transmittance prediction memory latency. Compared with the edge GPU, the accelerator achieves 6.3 to 10.3 times speedup for rasterization plus sorting. For end-to-end rendering, the speedup is 4.0 to 5.5 times because projection remains on the GPU and is not accelerated by our design. Energy results show the same trend. For rasterization plus sorting, energy saving reaches 16.2 to 31.9 times over the edge GPU. These improvements come from fewer rasterization MSCs, removal of explicit sorting hardware, and higher utilization through the unified PE array. A natural question is whether Axis-shared rasterization can simply be implemented on a GPU. On an RTX 3090, the GPU implementation gives only 1.22 times geomean speedup, while the dedicated accelerator reaches nearly 1.6 times for the same optimization. The reason is that 3DGS rasterization is not a gem-like workload, so it cannot fully exploit tensor cores. Sharing Axis terms on GPU also requires shared memory access, synchronization, and extra register pressure. The accelerator avoids these overheads by fusing shared term computation and combination through a register-to-register data path. This shows that the optimization becomes most effective when the data flow and PE structure are co-designed. To conclude, efficient edge 3DGS rendering requires algorithm hardware co-design. We identify two main bottlenecks: redundant computation in rasterization and scalability plus imbalance issues in sorting. We address them with three techniques. Axis-shared rasterization removes redundant axis-dependent computation. Order-independent transmittance replaces explicit sorting with lightweight decay factor prediction. The unified reconfigurable PE array supports both rasterization and MLOP inference with high utilization. Together, these techniques preserve rendering quality, reduce rasterization MACs, eliminate costly sorting hardware, and enable efficient 3DGS inference on edge devices. Thank you. I would be happy to take questions.